Waiting for someone, or are we just starting?
Let's just start, I think.
Okay.
All right. Hello, everyone. Thanks for coming to our final seminar for the year. Stepan has kindly agreed to take us through this final seminar, and he'll be discussing, well, mean curvature flow with surgeries for two-dimensional surfaces in R3, but I presume also making some comments about how it compares to what happens in higher dimensions. Thank you, Stepan.
Yes, thank you, Tim, for the introduction. Yes, the title is perhaps a bit leading. I want to start with mean curvature flow for the hypersurface embedded in Rn+1, where n is greater than or equal than 3. So I'm going to get to the case n equals to 2 in probably 10 minutes. I just want to quickly summarize how the argument works in the general setup for n greater than or equal than 3. So first thing I want to mention, we are dealing with immersed hypersurface, which is something that's gonna be problematic for n equals 2, and we're gonna need to switch to embedded. So that's, I guess, the first difference. Immersed surface. Okay, so let me just quickly summarize how the argument works for the mean curvature flow with surgeries for n greater than or equal than 3. So we have 3 a priori estimates with convexity, estimate, cylindrical estimate, and gradient. You've seen this probably too many times by now. And they all claim that basically that there exist some surgery parameters such that, and for the convexity estimate, we have that for each delta, roughly, I'm not being very precise here, but for each delta, there exists some C delta such that our lowest eigenvalue is bounded from below by minus delta H minus C delta, where the C delta depends on the initial hypersurface. For the cylindrical estimate, we have that for each eta, there exists C eta, such that whenever the first eigenvalue is small enough, but it means it's more than eta times the mean curvature, then any two other eigenvalues are close to each other. So by some C, it just depends on the dimension, H squared eta plus C eta. This is for ij greater than or equal than 2. And the gradient estimates just says that there exists, let's say, gamma 2, gamma 3, such that the gradient of second fundamental form is bounded from above by gamma 2, second fundamental power 4, plus gamma 3. And this is just, this r to the negative 4 is just some scaling constant. It's not really important. Okay. And today, I would like to focus on the this part right here, that there actually exist surgery parameters such that these estimates hold. We've kind of skimmed through that in this case, in the case n is greater than or equal than 3, but in the case n is equal to 2, there's actually some additional work that needs to be done, and I'm gonna mention exactly the problems that occur a bit later, but maybe just first quickly finish the idea of the main proof for the classical case, let's say, for the case n is greater than or equal than 3. So given these estimates, we can actually prove something called neg detection lemma, which very roughly says that there exists some bound on our mean curvature such that whenever maximum mean curvature, let's say at time t0, hits our threshold h star, then there exists a neck. Maybe just remark, or MT0 is convex. If our surface is convex, then there is no neck, but the surface is convex, and there are not any problems, because we know that mean curvature flow deals with convex surfaces pretty nicely. Here I would like to emphasize that this is more delicate than it may seem, because we need some surgery parameters such that we prove the estimates. And with these estimates, we are proving the neck detection lemma that guarantees nice surgeries, that guarantees sufficiently nice necks that we can do our estimates after the surgery as well. And this is obviously, this is like circular proof, which is not very valid. But the key thing is that with enough attention to detail, we can actually find surgery parameters that are better than some threshold, such that these estimates will hold. And then the neck detection actually gives us the necks which are sufficiently nice that these parameters are fulfilled. These surgeries are sufficiently nice. So it's quite delicate. Okay, and given the neck detection lemma, we can prove something called neck continuation lemma, or maybe theorem, which again, very roughly, I'm gonna put it in quotation marks, says that all necks can be extended such that they end with convex cap. By that I mean that we have something like this. So we have here our neck, and it ends with a convex cap, which is quite nice because we can just get rid of the whole region. Or it ends, or they end with small curvature. By that, I mean that the necks are gonna enlarge such that the area where we are performing the surgery has sufficiently small curvature, and thus the mean curvature overall will drop right after the surgery. Okay? And given these two theorems, we have the main theorem, which basically says that there exist H1, H2, and H3, such that we are given some hypersurface, let's call it M0. We're gonna evolve it under the flow until we reach some threshold for our mean curvature, so such that H max is equal to H3. Then we're gonna use neck detection and neck continuation such that we detect nice enough necks and we can perform surgeries. And then what we do, we discard regions that are isomorphic to Sn minus 1 times S1, or they are isomorphic to Sn. Okay, this exactly means we are getting rid of the surfaces which we know how they look. We can get rid of them, and the result of this procedure is that the maximum mean curvature drops below H2, and we can repeat the whole process. Okay, so this is just very roughly the key ideas in the proof that mean curvature flow with surgeries will terminate after finite amount of time. So just maybe go for it once again. We need some a priori estimates, which are right here. And they are a bit better than the a priori estimates for mean curvature. We actually need that there are surgery parameters, that under these surgery parameters, these estimates are preserved. We prove some neck detection, neck continuation, and with these two theorems, our main theorem works, roughly speaking. Okay, and now let's get to the case n equals 2, and there are some main problems why this algorithm doesn't work. So I guess the problem number 1 is that we need to drop the immersed condition, and we need embedded. This was highlighted by Vishnu, I believe in the previous talk, or maybe one before that we can have something called a Grim Reaper as a blow-up limit, and it's not behaving very nicely. But if we restrict to just embedded hypersurfaces, we cannot get a Grim Reaper. So that's one problem that's kind of solved by just restricting to embedded hypersurfaces. Then we had convexity estimate. The convexity estimate turns out to work, which is nice. So we don't need to deal with that either. But the cylindrical and gradient estimates are the ones that cause the problem. They actually stop working. And what needs to be done, we actually need to introduce new quantity called inscribed and outer radius. It's going to help us control our hypersurface and provide some analogs of the cylindrical and gradient estimates. So again, just to recall, we have something called inscribed radius. I'm going to denote this R in, and we have outer radius. I'm going to denote this R out. Okay, and roughly what this means is that inscribed radius is basically we are given some hypersurface, and the inscribed radius is the biggest ball we can fit inside our hypersurface, and outer radius is the biggest ball or radius of the biggest ball we can fit from the outside to our hypersurface. So something like this, probably. Maybe you can note that if our hypersurface is convex, this would actually imply that outer radius is infinity, right? Because we have something convex, so they can be arbitrarily big ball from the outside. Okay. And okay. And with this, we also introduced the new condition, a constant that's gonna control our hypersurface. So maybe something like a definition. The hypersurface M is called alpha non-collapsed if infimum of our mean curvature times the inscribed radius is greater than or equal than alpha. So basically, our balls are bounded from below. Okay. Well, since okay, maybe small remark. I'm gonna use sometimes the notation that inscribed radius, 1 over inscribed radius is the same as me, just a notation. Okay. I mean, okay, so it's pretty clear that if we are given a closed hypersurface, since the inscribed radius is continuous function, it attains a minimum, and thus our hypersurface is, of course, alpha non-collapsed for some alpha. But what has been shown, for example, by Ben Andrews, is that this I'm gonna write it down, alpha non-collapsedness is preserved by mean curvature flow. This is very handy. I mean that this
just a typo there with your collapsedness spelling. Very minor.
Actually, what is I just call that? Collapsedness, I guess. I'm not sure actually how to spell it. Sorry.
No worries.
It's just a D. A D's missing.
There's D. Okay, collapsedness. Write it.
It's not mathematical.
Okay, so just the constant alpha is preserved, let's say. Alpha is preserved. That. Oh, thanks. And yeah. Okay. Yeah. So the alpha is preserved. So this means that our ratio or product right here is preserved, or at least the lower bound is preserved under the mean curvature flow. That's nice, and it's going to be useful later. Okay. And okay, now to the estimates. So something similar to the cylindrical estimate that was proved by Vishnu, I believe 2 seminars ago. He proved that when we have alpha non-collapse hypersurface, then for each delta there exists C delta such that the mu is less than or equal than 1 plus delta times h whenever the mean curvature is greater than C delta. Okay. This is why is this a cylindrical estimate? Well, that's because on the cylinder, the 1 over inscribed radius is actually equal to 1. Equal to h, to the mean curvature. And it has been shown, I believe, later by Haushofer and Kleiner that given sufficient time, this product, this mean curvature times inscribed radius, actually converges to 1, given sufficient time of the mean curvature flow. And also that h times the outer radius converges to infinity. Which means that roughly, if we're gonna let our surface evolve, it's gonna form this cylindrical shape given enough time, which by the way has quite nice consequence. I'm gonna put this in bracket, but this implies that any ancient flows must have this exact ratio. H time R in must be 1. H time R out must be infinity. This is quite interesting consequence. Okay. So this is something called a cylindrical estimate. In our case, n equals 2. But in the Vishnu proof, he was using that we have non-collapseness constant alpha. And what it turns out that the alpha constant is not preserved by surgeries. I'll write it down. So the constant alpha is not preserved by surgeries, which is quite a big problem because we would like to have this estimate throughout our mean curvature flow with surgeries, but the alpha might deteriorate under surgeries. So that means that after the surgery, we no longer have this estimate. So that's a problem. This is a problem. And I'm gonna show the solution to this problem in a minute, but first, let me remind the gradient estimate that Vishnu has done. Okay. Again, there were some conditions. I'm not gonna mention all of them, but the important ones are that the infimum of h times r in and h times r out is greater than or equal than alpha. This means it's alpha non-collapsed, but also we have balls from the outside with that has this ratio at least alpha. Sometimes these flows are called sometimes called alpha induced in the literature, I believe. And also we needed that in parabolic neighborhood, let's call it P x0 t0 r, there exists a constant ck such that supremum or derivatives of our second fundamental form, possibly on a smaller parabolic neighborhood, sigma r. Sigma is something between 0 and 1. Is bounded from above by ck r minus k minus 1. So this is gradient estimate. And again, we have similar problem. We are relying on alpha non-collapseness from the inside and from the outside, which, as I mentioned before, this is not preserved. And furthermore, we are requiring that the flow exists in some parabolic neighborhood, which is again a problem because right after the surgery, we kind of don't have the history of our flow, and thus we cannot use this estimate. So again, after the surgery, this estimate breaks. So maybe just problem breaks right after the surgery. So these are the two problems I want to focus on today. How we will get rid of them. Okay, but maybe are there any questions so far? Does it make sense?
Sorry, do you have any kind of explanation as to why alpha is not preserved? Because don't you put in spherical caps? And don't spherical caps? Yeah, I was just alpha. I was expected to be preserved because I mean, if you have spherical caps, then alpha is 1 on a spherical cap. So maybe it's more.
Yeah, I'm gonna mention that in a second, but there's actually a theorem that it's gonna deteriorate, but the proof that Huskin and Brendel have done, they show that it deteriorates arbitrary small amount, but still deteriorates.
Okay.
So the spherical caps are kind of not enough. Okay, just spoiler, this is gonna be resolved by the fact that if we let a cylinder evolve, it's gonna actually make the estimate a bit better. So it's a bit better than alpha non-collapseness. and thus right after the surgery, we just deteriorate only a tiny bit, and the alpha actually will be preserved. We just need to do some work. But by the classical surgeries, the constant deteriorates.
Okay, thanks.
Yeah, sure. Good question. Okay, any other questions? Okay. Okay, so major thing that's going to be very helpful is the theorem 2.2. It's called pseudo-locality principle. Okay. And it says that there exist beta 0 and c, some constants, such that if we assume our mean curvature flow for some t 0 and t is a regular mean curvature flow. And regular, I mean just smooth without surgeries. In some neighborhoods, I think that in the statement they're using ball of radius 4. And this is important part, M0 can be expressed as a graph of a function u. Then if u is sufficiently continuous, so let's say in C4 greater than B0, then we have this nice estimate. The second fundamental form plus its gradient, second derivative, it's actually smaller than or equal than C for all these, either for the whole existence of the flow or from 0, beta 0. But this doesn't really matter how far is it. It just means that for small amount of time, right, which we're going to apply the pseudo-locality principle right after the surgery. So just maybe a sketch. So we have some neck. I'm gonna cut it and insert spherical caps. And here we can use in some ball. In some ball, the spherical caps can be modeled as a graph of a function, and we can use this estimate, which is gonna help us with this first problem, with the second problem, sorry, rather right here. Actually, right after the estimate, we can use the pseudo-locality principle instead of the gradient estimates that were proved before. So for some small amount of time right after surgery. Okay. And the pseudo-locality principle, it's modified. It can be modified, which is I'm gonna maybe quickly write the modified version for rescaling. That there exist beta star and C star with similar conditions as before, but what we'll get, the estimate is going to look a bit differently. It will be using this H1. I'm just going to write it down. H1 -2 gradient plus H1 3 from C star. And this actually holds for all t inside T0 and T0 plus beta H1, and for all x in MT0 intersected, or maybe MT, sorry, intersected with some ball around x0. Here I'm using that x0 t0 is point on the modified version. Sorry, on the modified region by surgery. So this estimate is just the rescaling of the pseudo-locality principle, but it says that right after the surgery, we have the estimate for our fundamental form and its derivatives in some ball. And very interesting thing about this estimate is that these constants, beta star and C star, do not depend on the surgery parameters, not even on the H1, which is the curvature of the neck on which we are performing the surgery. So this B star, C star are invariant for the H1, which we're actually going to choose later. Like if you would do the proof formally enough, H1 is chosen later. So this is for any H1 such as we perform a surgery on a neck.
Just to clarify there, Stepan, is it true?
Mm-hmm.
Is it so? You're saying it's true for all H1, not just all sufficiently large H1?
Yes,
or
for all
any
H1.
H1.
I mean, provided that this surgery is performed on a neck which is curvature H1, and then this estimate holds.
Curvature at least H1.
Yeah, I would say just curvature H1. I guess it can work for bigger necks as well.
Okay.
This estimate, but yeah, I was thinking that we have, yeah, good question. So I was thinking of a neck that has a curvature H1 in the region we are actually cutting and inserting the cap. Yeah, thanks for the question. Okay. And this actually, well, maybe, so assuming we will deal somehow with the alpha, which I'm going to mention in a second, how we deal with that. But assuming we deal with the alpha, by that I mean that we solve this problem right here, that the constant alpha is not preserved. But if we somehow manage to preserve the alpha after surgeries, we have actually solved the problem for the gradient estimate. So assuming alpha alpha problem is solved, we can found some C hash such that we have these estimates on the first and second derivative of second fundamental form. This is C hash H plus H1 squared and C hash H plus H1 cubed for all x's. And so the proof is, I mean, if you believe the pseudo-locality principle, the proof is quite straightforward. Basically, right after the surgery, we use this modified pseudo-locality principle, and after this time, beta H1, we can use the original gradient estimate that was given by Vishnu last time, I believe last time. So there we have the estimates which are given in the parabolic neighborhood. So after some time, we can use the gradient estimate that was given, and right after surgery, we use the pseudo-locality principle. So that kind of checks this problem. Does it make sense? Are there any questions? Okay, so if not, let's go for the second problem. So as I mentioned before, there is theorem 2.5. And just again, I'm gonna keep it a bit sketchy because there's not enough time, and I want to give the idea what's happening. So theorem 2.5 says, actually, sorry, one more thing before theorem 2.5. Sorry. So in the first problem right here, for the if you want to apply the gradient estimate, we need both both non-collapsing principles. So we need the inscribed ball radius times mean curvature is at least alpha, and also that the outscribed ball times the mean curvature is at least alpha. So there are two quantities we need to take care of. And the second one, the outer radius, is actually quite easily dealt with. So in the paper by Hudecek and Brendel, it's actually done with really simple condition that what they require from their necks. So their necks require one extra condition, which is given by the following. So for neck n, we require that this set x plus a times me x, so in the perpendicular direction to our neck, for each x in our neck, and for each alpha that's between 0 and 2 alpha hat r. I'm gonna mention what are those in a moment. So this set is actually disjoint with our surface, right? So this is pretty straightforward. If the surface is far enough, you can fit the balls from the outside in there, and there's no problem with that. And what are these constants? Well, alpha hat is any constant that's bigger than alpha, where alpha is our non-collapseness constant, and r is the radius of our neck. And surprisingly, the neck detection lemma in this case give us exactly these necks that satisfy this condition, and thus the outer radius is taken care of. So this part was quite easy. And for the inscribed radius, it's already started. I'm gonna need the theorem 2.5, which again, so it says that there exists delta 0 such that for each delta hat, such that they are in this ascending order, given alpha hat, delta hat, and epsilon L, those are just parameters for the neck. So given alpha hat, delta hat, epsilon L neck, and we perform surgery on this neck, the resulting surface is 1 over 1 plus delta non-collapsed. Okay, just so I already mentioned that this alpha hat is any constant bigger than alpha. Delta hat is actually constant of the non-collapsedness of the neck. So 1 over 1 plus delta hat, maybe. So the neck is 1 over 1 plus delta hat non-collapsed. And epsilon is just that it's sufficiently smooth, and L is the length of the neck. That's not really important. The point is, right here, that our non-collapsedness constant has dropped. So it started 1 over 1 plus delta hat, and now it's 1 over 1 plus delta. And since delta hat is more than delta, and just it's obvious, but this implies that 1 over 1 plus delta hat is larger than 1 over 1 plus delta, right? So our constant has dropped, and this is for arbitrarily delta hat. So as I mentioned before, for the Vishnu question, the deterioration is arbitrarily small, but it will deteriorate. So that's the problem. But what it turns out, again, it turns out that under some mild assumptions, yeah, so maybe like that. So our neck is approximately some curve times interval. So it evolves similarly as curve shortening flow for gamma. And what Hudecek and Brendel have shown that for each theta and delta, there exist delta hat in 0 delta, such that given a curve gamma t is from -2 theta to 0, and this gamma t satisfies curve shortening flow, which is basically mean curvature flow in 2 dimensions. Then if gamma t is 1 over 1 plus delta non-collapse, sorry. And there are also some conditions on outer radius, but these are satisfied in our case. This implies that gamma 0, which is at the end of this curve shortening flow, is 1 over 1 plus delta hat non-collapsed. Okay. So just to summarize, we have our surface that has non-collapsing constant alpha. I'm going to denote alpha 1 over 1 plus delta. So the non-collapsing constant is 1 over 1 plus delta. We have formed a neck, and I would like to do the surgery, but we know that when we perform the surgery, the constant is going to deteriorate. So what we do, we let this evolve by mean curvature flow, of course, because that's our flow. But this looks like curve shortening flow because our neck is just gamma times minus L times L. And this results in the non-collapsing constant 1 over 1 plus delta hat, which is better constant than 1 over 1 plus delta. And now, thanks to, and this can be for arbitrarily small amount of time, because it just gets better at least a bit. And the tiny bit that it gets better is enough for us. So now using theorem 2.5, we can get back to 1 over 1 plus delta, right? Because we mentioned that if we have neck with 1 over 1 plus delta non-collapse constant, we can get 1 over 1 plus delta for arbitrary delta hat delta. So by this scheme, it actually shows that the alpha constant is actually preserved by the flow, and that should be solving our second problem, that the constant is not preserved. So it's not preserved a priori, but we can make these tricks and it will become preserved. And thus, we have cylindrical estimate and gradient estimate that actually hold with the surgeries. So now it's the same thing as last time. We prove neck detection and neck continuation. There are some differences in the proofs, but we don't have time, and we haven't seen them in the original case as well. And these two lemmas will provide us with H1, H2, and H3, such that the mean curvature flow will terminate in the finite amount of time. Okay, there's maybe one small remark from me before I end this talk, which I found quite interesting. It turns out that if we send H1, H2, and H3 to infinity, the mean curvature flow with surgeries will converge to level set flow, which is something which is exactly weak solutions for the mean curvature flow.
Hey, Stepan,
Yeah.
do you know what sense in which the convergence is? Like what topology?
Ooh. I think I've got the paper here somewhere, but I'm not sure.
It's okay if you don't know off the top of your head. Just
I
curious.
don't.
Because it can't
Sorry.
be C2 or anything, right?
Yeah,
Has to
probably
be-
not, but
Is it Lipschitz?
uh,
Don't know.
I don't know. Sorry.
It's okay.
Yeah, I think I've got the paper somewhere, but I guess I can look it up later. But yeah. So yeah, it's pretty much end of the talk. Maybe I can mention what levels its flow is, but so I'm not sure if everyone is familiar, but yeah, that's all from me. Thank you.
Thank you, Stepan. I think
Thanks.
that Tim has disappeared. Tim, do you exist? Well, I think Tim's telephone may have run out of battery,
Yeah.
so I'll just
Would
take
like
over.
it.
Thank you for the very nice talk. Are there any questions? No, in that case.
Yep.
I guess this is the last talk for the series. So I would like to thank all the speakers and everyone who's been turning up. It's been a bit longer than we thought going through this topic, but it was really nice to see lots of details, and then also, of course, we didn't actually see all the details for a lot of things, but it's just a very large undertaking, surgery. So yeah, that's it. There aren't many people here right now, but just for you guys, I guess, we're planning on combining the online seminars with maybe some in-person events next year, maybe 2 per year or something, where we might try to get together and just have a day of a few talks and things. So
That sounds good, yeah.
Yeah, I think it would be really great to meet up again. We used to, in the past, have these New South Wales analysis seminars, and they were a really good way of just getting people together and catching up. And it would include like ACT people, of course. And often we would invite, like, for example, some people from Queensland as speakers to try to get everybody together and, I don't know, just catch up.
Maybe, Glenn, before we discuss that, I think I mean, Tim is not here, Paul neither, but I think we should also thank the organizers of the seminar, right? They did a tremendous job, especially Tim, who was like a big driving force, I imagine. Unfortunately, he's not here, but we can tell him. So let's thank you as well, right? I think it
I
was very
agree.
successful.
Thank
you.
you, Tim,
Yes.
very much.
The spirit of Tim is happy to hear those
Yeah.
words.
The spirit of Tim is thanked.
I think I think that's a very good idea, Glenn. Yeah, Tim mentioned the other day. I would make my best effort to make it. I don't know if he mentioned already, but
Yeah, he did. He said you have some very pressing matters to attend to at home, which is very understandable.
yes. But maybe a one day thing can be negotiated. I'll have to see. Yeah.
Yeah, it would be very nice to see what people are up to and thinking about. Just to catch up mathematically. We'll see. But yes, stay tuned to see what we're going to do next for the seminar, but we're not planning on stopping anything. We'll just pivot into the next thing.
Are we seeing any of you at UQ in December?
I'm coming.
I'm coming as well.
Nice.
Excellent. Yeah.
I'll be there.
Cool. All right.
I think I should
Thanks,
probably
Stepan.
stop recording. Am I able to
think
stop recording?
You're the host, Stepan.
Oh, I'm the host. Okay, sorry. I have never actually recorded, so I guess stop recording.